JMSL's TuningET class allows the user to define equal-tempered tunings. 5 values determine a equal-tempered tuning, and that is the reference pitch and the frequency to which it corresponds, the number of steps per octave, the octave ratio, 2 to 1 in most cases, and an octave stretch in cents. That is the number of cents that the distance of an octave increases every time you go up. In this example, you'll hear a chromatic scale ascending, and you'll be able to add an interval below it and an interval above it using these two gadgets. So let's listen to what 12-tone equal-tempered chromatic scale sounds like. This is going to be super familiar. So that's just like going up every fret of a guitar for 1 octave, or going up every key on a piano between C and a C above it, for example. Let's do something a little different. Let's split that octave up into 5 equal parts, not 12. And this is not going to be the same as a pentatonic scale chosen from 12-tone equal-tempered pitches. This is actually taking the octave and splitting it into 5 equal parts. So the frequencies you're going to hear would fall sort of between the keys of a piano. This is what I mean. So there's your 12 tones. Let's listen to what octave stretch and cents will do to this sound. Since the tone has an octave below and an octave above it, you're hearing that octave stretch and cents, creating this nice sort of warbling. Let's say the octave ratio was not 2 to 1. Let's say we came up with a theoretical octave that was 3 to 1. So that going from the first scale degree up an octave would actually end up being landing you on a frequency 3 times higher, not 2 times higher, but 3 times higher than the originating tone. Or an octave ratio of 4. You could use any values you want. So let's say a 17-tone scale. And let's say an octave ratio of 2.5. So you could create these synthetic scales for yourself and write pieces in equal temperament that most people have not heard before.